And now, to bring it all together, I give you part 4 on hypothesis testing. Let's start by recapping the problem. Is the true mean height of Sasquatches really 8 feet when our sample of 10 random sightings gave an average of 7.54 feet? And as we've covered before, this difference itself is not enough to say one way or the other, because the difference could just be due to the variance in the Sasquatch population's heights itself. It could be due to sample error. So to solve this problem, we first need to calculate the likely range of means that could be expected for a random sample to arise out of the variance in the population alone. In part 3, with our exploration of the central limit theorem, we learned the precise mathematical relationship between a population's variance and the variance then in that population sample means curve. That is, in the normal distribution of means you'd expect to see when you take random samples of some fixed size from the population. We saw how it worked for coin flips, and now it's time to apply it to our height data. The entire 3-step logic here, which we've seen before, is a simplification of the more formal and precise logic of statistical hypothesis testing, which we'll cover in part 4. The basic method is, if that mean of 7.54 we randomly sampled was unlikely enough under the assumption of an 8-foot mean, unlikely enough according to a predetermined probability threshold, that the assumption no longer seems tenable, we can reject the idea that the true mean height is 8 feet. So hypothesis testing is basically a process of giving a claim the benefit of the doubt, assuming it's true, before seeing if inference from our sample data can rule that claim out. Before diving in, it's worth taking a closer look at one point in particular that's easy to miss. What we're up to is called parametric testing, which means statistical testing that takes parameters. That is, our analysis proceeds through data summary measures, parameters, of mean and standard deviation, which we use to build a model we can ultimately calculate probabilities from. But you might have noticed already, in slowly learning the pieces of this method, that there are several symbols floating around for mean and standard deviation. There's S, there's sigma, there's mu, there's x bar, and there's 4 distinct distributions we've been using which take these different parameters. So it's crucial to keep them all organized in your head. So let's recap. These 4 distributions and their parameters are, first, the assumed population distribution with mean mu and standard deviation sigma. Second, there's the observed sample distribution with its own mean, x bar, and its estimate of standard deviation, s. Third, you have the modeled population distribution, which is built from the previous 2. So it takes the assumed population's mu for mean, and then either sigma or s for standard deviation, depending on what's known. If sigma is known, you use that in the model. If not, you estimate it using the sample's s. Fourth, you have the assumed sample means distribution, or what we've been calling the SMC. It has a center mu, but then has a standard deviation we call standard error, which is the assumed standard deviation, s or sigma, over the square root of n. The SMC, of course, is derived from the population model, and itself models the means of samples taken from the population. Note that the normal model in general, and z-scores, can be applied to any of these distributions if they are normal. But the first 3 distributions don't necessarily have to be normal. However, the central limit theorem, as we saw, has it that the SMC will be normal. So 4 is always normal. And this is where we'll use z-scores in hypothesis testing. We'll use them to find the normal probability that a particular sample mean would arise out from the assumed population parameters. Here's an illustrated guide to how these 4 different distributions are used in parametric testing. First, we have the population distribution. The majority of the time, only mu, the assumed true mean of the population, which is the parameter we want to test, is known. But usually, sigma is not. So we only have a line for mu, and we can't map out the entire population distribution. But here's our sample distribution. It's your random and partial cross-section of the population, and it's not necessarily normal. So note the irregular frequency curve that I've drawn. The sample's mean is x bar, and its estimate of sigma is s. Note here how x bar turned out to be less than to the left of mu, the population's assumed mean. So this could represent a situation like our Sasquatch problem, where we're assuming a population mean of 8, but then sampled a mean less than that. Next, we have our population model, which we build using the population's assumed center mu, but since sigma is not known, we use S from the sample for the model's standard deviation. Once we have the population modeled with its two parameters, the central limit theorem gives us the sample means curve, or SMC. That is, the predicted distribution of sample means from the modeled population. And according to the CLT, first, the SMC will have a center of the original assumed mu and a standard deviation called standard error equal to, in this case, S over the square root of n. Second, the distribution of expected sample means will be normal, even if the population is not. If we look to our sample as any indication of the population distribution, we can see it's not normal. However, I should clarify at this point this will be normal statement I've been using. You can trust the SMC will be normal if n is greater than about 20. But as long as n is 20 or more, the fact that the SMC is normal means, importantly, that our parametric hypothesis test will still be robust and reliable even when the original data is not normal. Therefore, we can use the z-score of x bar here on the SMC to check the probability that a sample would have x bar's value, or less, assuming the true population mean is mu. Logically then, if this probability of getting a sample mean of x bar or anything less, represented by the blue tail here, if it's too small, we'd reject the idea that mu is the true mean after all. In written steps, here's the full method for a hypothesis test of mean. It might look like a lot, but once we go over each step, it's not too laborious, especially, as we'll see, with technology like the statmagic app to help. I put the list here for reference. Let's start with step 1. So far, we've had a working definition of unlikely as having a less than 5% probability. And along with this, we've said there's a 95% likely range, with the leftover unlikely probability split evenly into 2.5% tails. We've also said the z-score marking this division was plus or minus 2. Well, in hypothesis testing, this concept of unlikely converted to a probability threshold has a formal name, alpha. And on a normal distribution, 5% in 2 tails has a more precise cutoff, plus or minus 1.96. Alpha, as a capture of what we think an unlikely probability is, can thus serve as a threshold of rejection. That is, it's the probability that we judge small enough to rule out the idea that chance is acting alone within our modeled assumptions. And therefore, it's what we use to rule in the idea that our assumptions are wrong. The 0.05 we've been using is conventional for this. So, if an observed sample mean, an x bar, were to have a z-score greater than plus or minus 1.96, that is, the x bar is in one of these tails, this means that its population with its assumed center mu had a less than 5% chance of furnishing that mean in a random sample. Therefore, if 0.05 was our threshold of rejection, our alpha, we'd logically reject the idea that the population assumptions are true after all. But this threshold of rejection can be changed to a higher or lower standard. For example, if alpha were changed to a higher standard of 1%, again, as a probability total for 2 extremes or tails, this leaves a 99% likely range, and it would require a sample mean in x bar to have a z-score on the SMC greater than plus or minus 2.58. So why change the standard? Why use a different alpha? Well, that depends on the question asked and the burden of proof that would seem appropriate for the question asked. This leads us into step 2 of hypothesis testing, which is determining the hypotheses and tails of the test. Here, after we've decided alpha, our overall probability threshold, we next need to spell out the precise event we want to measure the probability of and compare that to alpha. So that involves examining our original question a bit more carefully, because did we want to know if the true mean of Sasquatch heights is A, just different from assumed, or B, greater than assumed, or C, just less than assumed? As I'll show shortly, these three different and more precise questions will change the hypotheses and probabilities involved. So normally, we need to parse our question into one of these three more precise options before looking at our data. Otherwise, different from choice A is the most conservative and robust, and is what we should use here since we've already looked at our sample data and noticed that our sample mean is less than the assumed mean. But even had we not looked, this would be our choice, since we had no prior reason to suspect that our sample's mean would only be greater than or less than the 8-foot assumption. This precise type of question forming has a standard logical form in hypothesis testing. It's called formulating the null and alternative hypotheses, HO and HA. So in our question, the null hypothesis is that mu equals 8. HO, that is, states the assumption, the value region for mu that you want to test, rule out, or reject. Now together, HO and HA, the alternative, have to be complete. They have to cover the full logical ground of what mu could be. Because if you disprove something, you've logically proven its complement. So if you've ruled out HO, you've logically ruled in the complement HA. So in our example, HA would be that mu does not equal 8. So again, we have the three options. This first one applies to our example, with a null hypothesis of mu equals 8, which implies an alternative that mu does not equal 8. This combination of hypotheses is known as a two-tailed test because a significant sample mean to either side of 8 would disprove the null hypothesis. In contrast are the one-tailed tests, which only test to one side of the mean, leaving the rejection region and all of alpha in one tail only. If you wanted to test whether mu is only greater than some assumption, you'd use a right-tailed test, one of the types of one-tailed tests. Here, you'd begin with the assumption, the null hypothesis, that mu is either equal to or less than 8, because if you can rule all of this out, logically that only leaves the possibility that mu is greater than 8. A left-tailed test, then, is very similar, but the mirror image. And a left-tailed test could be applicable to our Sasquatch case, where we saw a sampled mean less than the assumption. But as we said, we need to select these hypotheses before looking at our sample data. And we'd only use a left-tailed test if we had a compelling reason to believe that we'd only get a smaller mean height when sampling the heights. So changing the precise question asked, changing the hypotheses of a test, changes its tails. Let's try to get a visual of what this means. Say our alpha is 0.01, and let's compare two cases. In the first, let's take a two-tailed test. Here, we'd reject the null hypothesis if a sample mean to either side of mu turns out to have had a less than 1% total chance of happening if the assumed population mean were true. In a second case, let's change this to a right-tailed test. Here, we'd reject HO if our sample mean turns out to have had a less than 1% chance of being sampled, but only to the right of mu. In this case, our observation x bar, our sample mean, would be signaling with less than 1% chance of error because of our alpha that mu is really, truly greater than assumed. Visually then, changing from 2 down to 1 tail, holding our alpha constant, changes the location of the likely versus unlikely ranges on the SMC. That is, a one-tail test shifts all of the unlikely range into one tail, since a sample mean in the opposite tail no longer would disprove our null hypothesis. The question we're asking now is only if the true mean is greater than assumed. So to see a sample mean signaling the opposite over here doesn't pertain to our question anymore. It's the hypotheses that we've set up that way. So a one-tailed test halves the number of outcomes which disprove HO from 2 to 1. But it doesn't change our total alpha, our total disproving probability. So alpha no longer needs to be split. Only one outcome, a sample mean greater than mu, can disprove HO, so it gets a lower burden of proof. We see a minimum test score of 2.33, marking a 1% tail, instead of 2.58 z-scores, which both mark 0.5% tails. This is why, methodically, it's important to choose a one or two-tail test before peeking at the data. Changing to a one-tail test after noticing the sample mean is greater or less than mu changes the conditional probability here, and it would make for a biased test given the lower burden of proof. In a stat class, you might be asked to determine or choose the tails of a test from a written question. I admit it can be tricky to translate a question written in English into one of the three HO-HA pairs. But my tip is always default to two-tailed as the most conservative unless there are keywords like greater than or less than that clue you in to a one-tailed test. With alpha and the hypotheses set, we can put together our population model with its assumed parameters. First, we set the model center to mu. Next, we need to set the population model's standard deviation parameter, sigma. As we've discussed, when we know or have a number to assume is the population's standard deviation, we use that number. But when sigma is not known, which is most cases, we have to estimate it from the sample with S. However, this step of estimation of standard deviation introduces a wrinkle into our parametric test that we need to address. So basically, like x bar, the sample's mean, as an estimate of the true mean, S as an estimate of sigma also improves as sample size increases. So when using S as an estimate of sigma, we need to check N to see how good S is as an estimate of sigma. And if N is too small, and conventionally less than 30, we can't be sure that it's guaranteeing a good estimate of sigma. So in those cases where N is small, less than 30, we need to use what's called a t-test instead of the z-test we've been using so far. So what is a t-test versus a z-test? Well, these are both types of a hypothesis test of a mean, but they differ based on the type of distribution we're using to model the sample means curve, the SMC. A t-test uses the t-normal distribution, where the z-test uses the z-normal. And that means that a sample means position on the t-normal is a t-score. So this is just like the z, except a t-test has something called degrees of freedom. This extra degrees of freedom parameter on a t-normal distribution ends up giving it fatter tails, which help control for the estimation error of using S to estimate sigma. A t-test is a more conservative test, but as n increases, the t-distribution starts to approximate the z. So you'll have to take my word for all that, because we're not going to dive into the math at this point. But the takeaway is, where n is greater than or equal to 30, we can be pretty sure that we've sampled enough so that S is fairly representative of sigma. And this switch at 30 to using a z-test instead of a t is conventional. If we were to compare where n is 30 exactly, the critical t-score for an alpha of 0.05, two-tailed, would give you n minus 1 degrees of freedom, or 30 minus 1 is 29, and that critical t-score ends up being 2.045. And you'll remember that this critical z-score for the same spot was 1.96. So when we're working with small sample sizes, we have to remember to use t-tests and their degrees of freedom. Now, you might be wondering, what is a degree of freedom? Well, it comes from the fact that we're estimating variance from another estimate, the sample's mean. that is, x bar, is part of the formula for calculating variance. It's a subtle topic, but you can think of degrees of freedom as, say you have 3 numbers, but they must add up to 10. So you could pick any number for the first 2 numbers, but once you have, that third number is predetermined, because it's 10 minus whatever the sum of the first 2 are. So this would be a situation with n minus 1 gives you 2 degrees of freedom. Technical points aside, let's focus on how we know when to use a z versus t-test. And this actually hinges on just one question. Do we have a good estimate of the population standard deviation? Well, first, if sigma is known, yes, we have the best estimate available, the true number, so we can use a z-test. But if sigma is not known, and we're here, then we have to look at, is our sample size big enough to be given a good estimate? And conventionally, if n is greater than or equal to 30, we can use a z-test. So, therefore, the only time we have to use a t-test is when we're using s and our sample size is small. It takes 2 no's in this little algorithm. Let's take our height data for an example. We don't know sigma, we don't know the true standard deviation of Sasquatch heights, and so sigma is not known, and n is only 10, which is less than 30. So the 2 no's say that we have to use a t-test in our Sasquatch heights example. One last thing to note here is that a test of binary data can always use a z-test, since, as we saw in part 3, the variance of binary data is already known. It's already hard-coded in its proportion of 1s. However, a z-test of a proportion is more reliable when sample size n times the mean or center proportion p and n times 1 minus p are both greater than 5. The fourth step in parametric hypothesis testing is to find the critical test value. And this is something we've actually already seen in our discussion of alpha and tails. The critical test value, notated with an asterisk, is the z or t score, or scores in two-tailed tests, that mark where alpha is on the SMC, and therefore where the unlikely versus likely ranges are on the sample means curve. Therefore, a sample mean with a z or t score more extreme on the SMC than the critical value puts that sample mean in the tail or rejection region and outside of the likely range. And this also means that it has a probability less than alpha, or less than alpha divided by 2 for two-tailed tests. So, for example, if our sampled mean Sasquatch height, 7.54 feet, ends up having a t-score greater than the absolute t critical value, this would indicate that 7.54 feet is an unlikely mean to sample, at least under our modeled assumptions. So, a z critical value depends on 2 things, alpha and tails. And a t critical, just like a t score, depends on these and degrees of freedom. So here's our illustrations of sample means curves again, where alpha equals 0.01, and you can see the critical values marking half of alpha in each tail for a two-tailed test gives you a z critical value of plus or minus 2.58. And you can see how that changes with tails. Going to a one-tailed test, where all of alpha is in one tail, means your critical value is only positive 2.33. For the very common alpha of 0.05, for a two-tailed test, your z critical would be plus or minus 1.96, and for a one-tailed test, about 1.65 for the z critical. For any t critical value, you need to incorporate the degrees of freedom. So to find a critical score for any alpha, tails, or z or t combination, you'd have to reference a z or t table, or use a technology like the statmagic app. Now, it's time to calculate the test score. And this is the t or z score, then, of the observed sample mean on the sample means curve that we derive from the modeled population. So let's rehash the logic of this. This is the logic of hypothesis testing, that we want to find the test score of the sample mean we observed, where it lies on the sample means curve that we're assuming to be true if the population is as modeled, if its center really is truly mu. We want to find the test score so that we can find the probability that we had of observing the sample mean that we did. So let's see this in steps. Again, the population model, we gave it an assumed mean, mu, what we're assuming to be true, and then we give it a spread, a standard deviation, sigma if it's known, but s if it's not, to estimate sigma. And then we know the central limit theorem tells us that our population, even if it's not normal, will have a normal sample means curve with a center mu and a standard deviation called standard error of sigma or s divided by the square root of n. Therefore, a test statistic of a sample mean on a sample means curve is, in general, the observed mean minus the assumed mean over standard error. So this tells you how many standard errors away your observation was from the expectation or the assumption. So taking our Sasquatch heights example, we need a t-score, and plugging in our observed mean versus expected over s. Remember, this is our sample standard deviation standing in for sigma, and I'm not rounding it yet, so I don't want to throw off our t-score. Divided by the square root of our sample size, 10, gives you a t-score of negative 2.3447. And remember, being a t-test, we also need the t-score's degrees of freedom. And for our sample, we have 10 minus 1, or 9 degrees of freedom. So what do we do with this score? Well, we're going to use it to infer the probability of seeing the sample mean we did if the true population mean is as assumed. In other words, just how likely or unlikely were we to sample a mean of 7.54 feet in a sample of 10 Sasquatches if their true mean height really is 8 feet after all? Once we have a test score, we know that it has a set probability. But to reach a conclusion with our test, we need to turn this probability into a yes or no. So step 6 in the hypothesis testing is to evaluate the test score and its probability against alpha and the critical value, and decide whether we can accept or reject the null hypothesis. So to see if we can reject HO or not, we have two equivalent options. We can, 1, compare our test score, the t-score that we just got, to the critical value, which was set by alpha in the tails of the test, or 2, we could compare the probability of this test score directly to alpha. So then, if the test score of the sample mean were to be more extreme than the critical value, or its p-value was less than alpha, we would reject the null hypothesis. So what does it mean to reject the null hypothesis? We're saying that based on the alpha threshold we set up in advance, plus our faith in the central limit theorem working, that the sample mean we observed was so unlikely to arise in a random sample of the population as assumed, if it really did have a center mu, that we now reject the idea that its center is mu. We're saying that we reject the idea that mu is the true center of the population. And since the alternative hypothesis, HA, is the logical complement of HO, when we reject the null hypothesis, we then conclude that there is statistical evidence for HA. We embrace the alternative hypothesis, that the true mean is either does not equal, is less than, or greater than mu, depending on the hypotheses we set up. Here's a quick visualization of rejecting HO by scores comparison. So in this hypothetical test, we had an alpha of 0.05, and we ran a z-test. And an alpha of 0.05, two-tailed, corresponds to a critical z value of plus or minus 1.96. And our sample mean had a z-score of 2.13, which is more extreme than the positive critical value. Note that a negative 2.13, the symmetric result, would have also rejected HO. With just scores comparison, we know that getting a test score greater than an absolute critical value means that the probability of getting that sample mean was less than alpha. But that's all the more resolution we get. However, if we have the means, like if we have the statmagic app, to calculate the exact probability, also known as the p-value, of that sample means test score, we can do that and compare the p-value to alpha directly and see if we reject HO or not. The benefit of this method is knowing the strength of the evidence, because the smaller the p-value, the more conclusive the evidence is. Just compare a test with a p-value that says an observed sample mean had a 1 in 20 chance of occurring randomly under the assumptions, versus a p-value that says it was more like a 1 in 1,000 chance. The second case is much more conclusive evidence. So here's our same hypothetical test as before, where we had alpha of 0.05 and a z-score of 2.13. Turns out that a z-score of 2.13 for a two-tailed test has a p-value of 0.033, or about a 1 in 33 chance of this sample mean being random. The last tricky thing to remember here is that in two-tailed tests, we have to, quote, double our p-values. That is, the probability of a sample mean having a z-score of positive 2.13 or greater is 1.66%. But in a two-tailed test, remember, we are determining the odds that a sample taken randomly from the modeled population would have a mean that is different from mu, not just that much greater. So we need to add in the probability of the symmetric result of the equal but negative z-score, and this doubles our p-value in a two-tailed test. In this test, the p-value is less than alpha, so we would reject HO, that mu is equal to some value, and conclude by accepting the alternative hypothesis, HA, that mu is simply not equal to that value, seeing how this is a two-tailed test. And this is the end of a typical hypothesis test. But there's one more very useful thing we can do with our sample data. Say you've run a test, rejected HO, and concluded then that the assumed population mean is not correct. So you might wonder, what is the true population mean then? Well, it's not x bar, the sample's mean. Remember, when an HO is rejected, the HA you accept in turn only tells you it's either not equal to, less than, or greater than assumed. It does not tell you exactly what the true mean really is. However, you can use the sample data to construct what's called a confidence interval. From the sample data, a CI infers the interval that we can be X% sure or confident contains the true population mean. Confidence intervals use the observed sample mean to estimate the true mean, instead of assuming some population mean is true. So here are the Z and T versions of a confidence interval. With a CI, you're not assuming you know the population's mean. So instead, you're using x bar, the observed sample mean, as the center of an interval for your estimate. You then use a critical value and the standard error to construct a normal interval around this point estimate, x bar. For example, if you wanted a 95% confidence interval, you would use 1.96 for the critical value, where a z distribution is appropriate, that is, under these conditions. Again, for both hypothesis tests and CIs, you are assuming that your estimate of sigma, the population standard deviation, is accurate, or else you have to use the t distribution to control for your estimation when sigma is not known and you have small sample size. So looking at these formulas, the greater the sample size, the smaller standard error will be. You'll be dividing by more n. And then the narrower the confidence interval will be. That is, it'll hone in on the true population mean along a normal distribution, thanks again to the CLT. But the more confident you wish to be, if you want to be 99.9% confident as opposed to 95, the smaller your alpha will be, and the greater your critical value, and hence the wider the interval must be for you to be that percent confident. How does this work? How can we be 95% confident that this interval centered around our sample's mean will contain the true mean? Let's think about our coin flip experiment from part 3 on the central limit theorem. For a random sample of 100 flips, we found a standard error of 5 tails, which told us that we're 95% likely to see between 40 and 60 tails when the true central tendency was 50. We got that likely range from 50 plus or minus 2 times the standard error. In other words, only 5% of our sample means in the long run are expected to be outside of this likely range of plus or minus 10 tails, of 39 or less, or 61 or more. But what if, for every random sample of 100 flips, you took its mean, x bar, as the best estimate of the true mean, and constructed an interval of whatever x bar was plus or minus that same 2 times standard error, that is, plus or minus 10? Well, with the simple math here, you can readily see that only those intervals with x bar centers of 39 or less or 61 or more would not contain the true mean of 50 tails out of 100 flips. That is, 39 plus or minus 10 gives you an interval of 29 to 49, and 61 plus or minus 10, 51 to 71. And these means, crucially, as we saw, only happen 5% of the time when the true mean is 0.5, or 50 tails expected out of 100. Thus, you can be 95% confident that for any interval constructed from any sampled x bar, it will contain the true mean 95% of the time. Therefore, this concept of confidence is really less like a probability and more like a logical guarantee that comes out of good random sampling methods. One final note on hypothesis testing and confidence intervals. A two-tailed hypothesis test of some alpha and then a 1 minus alpha confidence interval can, quote, agree. That is, if the hypothesis test rejected the assumed mu as the true population mean, then the CI will not contain the assumed mu. On the other hand, if the test failed to reject, the confidence interval will contain mu. So whether or not the interval contains mu can be another way of accepting or rejecting HO. A couple of graphics should help clarify this point. So in this first graphic, we have a nearly significant result for a two-tailed test with an alpha of 0.05. You can see that the observed sample mean, x bar, is still just to the inside of the likely range on this modeled population's sample means curve. It's just inside by this red amount. This means that on the 1 minus alpha confidence interval, which takes x bar as its center, it will still contain that assumed mu, which is inside the interval by the same red amount. This makes sense because mu and x bar are the same interval apart. But again, this is only true if the test is a two-tailed test, because a confidence interval is always two-tailed, at least in our case. Therefore, they use the same critical value, and they always also use the same standard error. Confidence intervals can be one-tailed, but this is not a common usage. So if, again, the difference between mu and x bar were greater than this common interval, as in a significant test, then the confidence interval would not contain mu. X bar would be outside of this likely range, and in the corresponding confidence interval, the assumed mu would be beyond the interval. Let's finally solve the Sasquatch problem completely. We'll use the statmagic app to help us visualize the population model and to take care of all the calculations. We can walk through it using the 6 steps we've laid out. First is to set the alpha, or the unlikely threshold. 0.05, the convention, is good. Second, we need to determine the test's hypotheses and tails. We'll stick with the currently selected does not equal, because we didn't have a compelling reason to think that Sasquatches are necessarily taller or shorter on average than Woodland Pete's claim, and we've already peeked at the sample data. Hence, we'll run a two-tailed test. The third step is to input our parameters, both for the population model assumptions and for the observed sample data measures. As we do, in statmagic, the population model graphic will fill out for us, and after we've entered n, show us the sample means curve. So first, our assumed mean was 8 feet. Our observed sample mean was 7.54. Our sample standard deviation, and remember not to round this number prematurely, and then we had a sample size of 10. Now we need to choose whether to use a z or t test. So going through our little algorithm, sigma is not known. We're using s as an estimate. And then n is less than 30, so we need to use a t-test. Note that if we were to leave z selected, the friendly warning message that pops up. Note how the graphic is modeling the population curve behind its sample means curve. As we've covered before, these two curves' relative peakedness around their center shows how strongly the population's central tendency should come out in the sample means curve. That is, how narrow of a range the sample mean should obey for any random sample of the entered sample size n. For example, this is what it would look like if our sample had been of 100 Sasquatches. Also note how there are two symmetric lines on the sample means curve, one marking x bar and the other marking x bar's twin extreme. This is because this is a two-tailed test. So we want to find the combined probability of observing a mean at least as extreme as x bar, that is, to either side of the assumed mean. So we want the combined area in the two tails marked by these two lines. Statmagic will do the rest of the steps for us. It'll find the critical test value, that's number 4. Number 5, it'll calculate the test score of the sample mean on the SMC, in this case a t-score. And number 6, it will accept or reject the null hypothesis and return the test p-value. It'll even do the bonus and calculate a confidence interval for the true mean. Just hit calc and expand to see all the results. We have a significant test here, rejecting Woodland Pete's authoritative claim with a p-value of 0.0437, which is less than our alpha of 0.05. And the t-score for our sample mean of 7.54 feet was negative 2.35 about, beyond the critical t of plus or minus 2.26 for 9 degrees of freedom. Note how the confidence interval at the bottom does not contain mu. It does not contain 8. The upper bound is just short of 8. It tells us that we can be 95% confident that the true mean height of Sasquatches is not 8 feet, but between 7.09 and about 7.98 feet instead. And finally, the key points from this part. We've learned that the statistical way we can challenge an assumed mean, having only partial data, only a sample, such as the question of the true mean height of Sasquatches, which has animated this series, is what parametric hypothesis testing is all about. And we saw how hypothesis testing makes use of everything we've learned from the first 3 parts. Data measuring, or descriptive stats, like mean and standard deviation, are taken as parameters in data modeling, especially using the normal distribution, which, the central limit theorem says, applies to the distribution of sample means, that is, the SMC, even from non-normal populations. Thus, we can use the fact that the SMC is normal, with a center mu and a standard error of sigma over the square root of n, to infer the probability of observing a sample mean that we did. And if it was unlikely enough, as predetermined with alpha, we then have statistical evidence to reject the assumed mean mu as the true mean. Lastly, we learn that where hypothesis testing can only tell us if the true mean appears equal to, greater than, or less than assumed, depending on the null hypothesis, a confidence interval can give us an estimated range of the true mean using only sample data.